First of all, thank you for the organizer to give me the opportunity to present my data here. And this work has been partially done at UCD here. And I will be talking about quartz this morning. Everybody knows that quartz is a well-known toxic particulate, and it's recognized again by International Agency for Research on Cancer as a main cause of silicosis. It causes lung cancers as well, and many autoimmune diseases. There are many occupational settings where workers are exposed to quartz, mainly mining, construction, or sandblasting, even clothes fabrication. All the settings where abrasion and rupture crystal are more likely to happen. But also, low doses and chronic low doses may cause diseases to humans. Quoting Ken Donaldson recent review, why we are investigating quartz, because we want to know the characteristic of particles that determine the ability to cause harm. And since, also, although quartz has been studied for 30 years, there's still a lot of things to know about it. In fact, quoting George Orwell here, all silicas are equal, but some silica are more equal than others. In fact, the flexibility of silicon tetrahedra, silicon oxide tetrahedra, and the covalency of that bond determines a large variability on silica properties. First of all, crystallinity and amorphous silica, that all you know, but also the origin of the dust, like all the process that the dust encounters in its life can affect the surface chemistry. And the intrinsic complexity of surfaces of silica and mainly quartz are very, very important in determining this pathogenicity of this powder. So maybe all you know that the chemical functionalities at the surface of quartz are very complicated. You can have isolated silanols or H-bonded, hydrogen-bonded, the geminal silanols, or even dissociated. All those features determine how water interacts with the surface and eventually are the main cause of the hydrophilic and hydrophobic character of the surface. And further, silica surface can bear a lot of reactive species. Every time we break a silica particle, we obtain a lot of reactive species that the surfaces, the newly created surfaces, are highly reactive, and then they encounter a surface reconstruction in a very short time. This is source of free radicals inside the organism when you breathe it. And recently, the modeling of those surfaces was attempted, and it has been reported that all those surfaces have different reactivity according to their crystal structure. For this reason, if you really want to go a little bit more in detail about the quartz pathogenic properties, we want to control this complexity. And then the way we think about it was to synthesize quartz, which is not trivial, but I'm trying to show you what we did. So we started from sodium metasilicate, which is the polymer component block. And then we choose opportune polymerizing agents. So we started the polymerization in a very classical way, and then we heated to make the crystal growth. So the classical pathway is you lower the pH, then you come in the stable range of a sol, and then you heat it to make the crystal grow. Definitely, basically the monomer polymerize, then you find yourself in a in a three-dimensional gel network. And this network is very important. To control the dimensional the structure of this network, it's very important to understand and to drive the crystallization process. In fact, all our polymerizing agents deliver a very good crystalline quartz in almost all the synthesis time. And another surprising fact is that we were obtaining almost also only alpha quartz, just one polymer. We wanted to go a little bit more in detail, so we investigated the crystalline cell of our quartz, and we found that they were differently stressed according to the polymerizing agents when they were compared to a standard quartz. So we have a nitric acid polymerizing agent that gave the most ideal cell structure, and CO2 and hydrochloric acid that were given a little more stressed crystals. We also checked the crystallite size, and again we see that the sample were differentiating. So we have two bigger crystallites and one smaller for hydrochloric one, and we also check the size of the particles of the that we obtained and surface area, and again differences were occurring here. So summarizing, our samples were in a kind of a matrix for several parameters, like we have high crystal misfit and high crystal quality and a big crystal size. For CO2 and hydrochloric acid was low and medium size, and nitric acid was very perfect crystal with high quality and the smallest in size. Now, we are trying to explain in those days why this happened, and what are we thinking is that we can controlling the host phase of the gel during the synthesis. The excess of sodium in the gel can create these species. Those species make a high reticular relationship with quartz, some of them, but others don't. This picture hopefully explains this. So if we compare the crystal cell projection of quartz with sodium carbonate, we see that we have a very nice match, a very low misfit. So that's why we think that carbonates help to crystallize quartz, while the other two don't. So another proof of this was given by Raman spectroscopy. In fact, we observed that carbonate-driven quartz is the black spectrum, just deliver pure alpha crystals, alpha quartz crystals. But when we don't have carbonate, we have hydrochloric or nitric acid, we have a mogonite phase, which is a cryptocrystalline form of quartz, which is helping to form the quartz in our system. And another important features we want to control making crystals, it's the surface population of silanols. So to investigate what we have done, we basically use infrared spectroscopy on supporting pellets of quartz. We investigate the surface as it is, and then we outgas it. So we remove water from the surface, and then we heat it again at 120 degrees, so to a temperature that removes water but doesn't alter the silanol population. What we have here is that the black curve represent the black spectra represent the bare surface without outgassing. Then, if we outgas in all the spectra, the amount of water it diminish, but to a different extent. And if you look at here, you have you see the appearance of isolated silanol at the surface, because you remove the water, then you can see the isolated silanol. But if we heat the sample to a higher temperature, only the quartz created with CO2 have a further step of water removal. This means that for quartz, we have, for carbonated quartz, we have the absence of isolated silanol, and the water is partially bound, only partially bound to the surface. For the other two, the water is promptly removed. This means that the hydrophilicity of the first one is higher than the other two, and this may make a lot of differences in terms of bio effect of this quartz. So we analyzed them, the morphology of those quartz, and also the morphology were quite different. So we have the big crystal that we investigated before from the CO2 driven one, and hydrochloric was the average, and nitric acid polymerized was the most perfect and smallest one. We added one sample to our metrics because we wanted to have a sample that have a surface area and a size close to a commercial quartz, like Minozil, the quartz that was largely used in toxicological studies on quartz. So we took another carbon dioxide created quartz, we milled it, and we obtained this one, which is very similar to a commercial quartz. Then this is the part that I've done in Dublin. It's we did some biochemical testing. So basically, we screened the particles for high content analysis, and we analyzed the uptake of the particles with bio-TEM. And we wanted to see if the serum protein were absorbed differently on the surface of those quartz. The uptake was surprisingly high for all those samples. So we found our crystals in all the macrophages experiment that we performed, and but no toxicity was recorded. This is important because remember we are talking about toxic particles, and usually we were expecting to have this kind of toxicity. But they still were differentiating according to lysosome acidification on macrophage cell. A lower response was recorded for epithelial cell. Interestingly, we had this trend with milled quartz with new surface, reactive surface was the most reactive on macrophages, then hydrochloric, then CO2, and then the most perfect one was the less reactive in all the tests performed. And we also wanted to see if there was a difference in protein absorption. So we incubated our samples and we did some SDS page on the hard protein corona. That means the protein irreversibly bound to the surface. And again, our sample differentiated. We have both high molecular weight and low molecular weight differences among the samples, if you can appreciate it from. And so this could be partially one of the reasons of the biological difference that we are observing, or just the reactivity of the quartz can be a reason. We are investigating that now in Torino. And so I will just conclude this with these three remarks. So we have been able to synthesize those nanocrystals and to drive through an assisted polymerization to drive different properties and to make them appear at the surface. We surprisingly obtained high purity quartz that it was not active in all the cells, not toxic in all cells that we were investigating. And we believe that differences in crystal size, quality, and surface hydrophobicity modulate the cell response and also the protein corona that we have seen. So there's a lot of things to do still on this field, but I will follow this experimental part for a long time still, I hope. So before concluding, I want to thank my group in Torino and the people in UCD that helped me a lot during this the July stay, my stay there in July, and QNano for the economic support and ENAIL here, Italian Occupational Health. But the logo was here, it disappeared. Don't tell them that its logo is missing, but ENAIL is to thank. Thank you for your attention.
you very much, Francesco's question already over there.
Yep.
Thank you, Dr. Turci, for this interesting result. So I'm really amazed that quartz nanocrystals do not exhibit toxicity. Was it cytotoxicity which was investigated?
Yes, it was investigated cytotoxicity on epithelial cell and macrophages, murine macrophages.
So this is similar to what is found with amorphous silica. With amorphous silica,
yep,
the toxicity is also severely masked by the adsorption of proteins on the silica surface. So if you remove these proteins, then suddenly the amorphous silica becomes cytotoxic.
Well, the first big thing is that we have a quartz surfaces that seems not to react badly with cells. That's a point. The reason, the detail, the chemistry behind that, it's still under investigation. Probably the findings on amorphous silica that are going on in those years can help to understand that behavior as well. But we are trying to build up our surfaces as simple as possible, just to be sure that we understand the mechanism behind what we are seeing. So probably protein absorption and removal can be one of those, definitely.
Jacques Bouillard in Aries. Are you trying to look at the cytotoxicity effect versus the specific surface area?
Well,
you find there's something.
Okay, all quartz, they have, except the CO2 synthesized one, they have almost the same specific surface. They were about 7, which is all the surface specific area of natural quartz grinded, like Minozil or Madagascar or DQ12. They all go around 7, 8. For some reason, which are crystallographic reason, the CO2, it's very flat and has a surface area of 1.1. And this was the most reactive in our test. So there's a kind of paradox. But we will investigate it further. Yes. The particle were tested as synthesized, so no mill. But we took one sample and we milled. And the milled sample was the most reactive. That's understandable. We know that when you crack a surface, you create radicals, you create defects, and all those defects can start the inflammatory response in a macrophage especially, but even in an epithelial cell. Yes, but the data here are not on milled quartz, except for the protein corona.
Okay, one last question? Or we move on to the last speaker?
So it's a bit puzzling. You're trying to look at the carcinogenity to explain of natural quartz, and you try to build crystalline quartz itself, and you see almost no effect between amorphous and crystalline quartz. Well, the common idea is, of course, that the crystalline is dangerous and the amorphous is not dangerous.
Yes.
So what's your idea about this?
Okay, the easy answer is the carcinogenicity of quartz and the inflammatory activity comes from fractured surfaces, which is quite possible, because whenever you fracture a surface, you create defects, you create free radicals that recombine easily, and they can bring a reactivity inside your lung. That could be, but still, this is not can be the only answer, because when you fracture quartz, the surface instant reactivity, it disappears in seconds or minutes, but silicosis and then lung cancer can develop in years even after exposure is terminated. So there is a gap to fill between the surface reactivity in a chemical way and the biological events that can become like they can bring to sickness or to cancer. The aspect ratio of the particles. Well, they were all a crystalline solid has its own aspect ratio. So all quartz crystal were elongated along the z-axis, and they. Well, aspect ratio, it's important when you go to asbestos, to that kind of to fibers. But quartz is not a fiber. It's not an isometric particle because it's not round, but it could have an aspect ratio of 2. And carbon nanotubes have 1,000, asbestos has 10, but it's very short, elongated particles. But I'm saying synthetic quartz is not toxic. Not that quartz is not toxic. Don't make me say that. No, I'm talking about these 3 samples. Thanks. That's why I went to UCD, and we are going again. Now, joking aside, it's surely are intriguing data. We want to go deeper in that, and the first thing that comes into my mind is the surfaces are clean and not reactive with respect to a milled quartz, like a regular quartz from an industrial setting, but. In Torino, I didn't show those data, no time, and we already checked for free radical reactivity of those surfaces, and we found some. So apparently there are some more complex things going on because we observed the free radical reactivity of the surface. So apparently they were able to induce an inflammation.
Okay, so some stimulated discussion.